Hello there and welcome back to this video series on control systems. In the previous two videos, we have considered electric circuits with resistance, inductance and capacitance in them, and we have also derived transfer function of RLC circuits. We have seen a couple of examples and we have seen how to derive transfer function of this RLC circuits. Going forth, we will consider mechanical systems, ones which involve spring mass damper systems, and we'll try to derive transfer function of such simple SMD systems, spring mass damper systems. As the name indicates, the kind of system that we consider will contain springs, masses and dampers connected either in series or in parallel. So what we will consider in the next subsequent couple of slides is what is a spring, what is the governing equation for spring, what if springs are connected in parallel, in series. Similarly, dampers, what is a damper, what is the damper force, what if dampers are connected in series and in parallel, and so on in an elementary way. Then in the subsequent video, we'll see one or two problems on that. A typical spring is represented as shown here, whose one end is fixed. At the other end you apply force and the spring undergoes a deformation xt. One end of the spring has a deformation x of t, the other end is 0. In such cases, the total force in the spring is spring stiffness K multiplied by the elongation of the spring. This constant K has units Newton per meter. If you take Laplace transform of this, you will have f of s is equal to K times x of s. Both f is capital, x is capital here. In passing, we may note that if this end also, instead of being fixed, it is also undergoing a displacement, that is xt displacement of one end, yt displacement of the other end. If it is happening, we'll slightly modify the equation. We'll say k times xt minus yt. Here f of s is k times xs minus y of s. In a system, it is possible that two springs be placed in series. That is, there is a joint such that the springs appear in a row, one is hooked up to the other, and a force Ft is applied at the extreme end of the spring. In such cases, we will find one spring which can substitute both these springs in series. That is called equivalent spring, and its stiffness is Ke, K equivalent. We'll write Ft is Ke of xt, where Ke is given by the rule shown here. We see that if springs are in series, the same force goes through the springs that are in series. Similarly, if the springs are in parallel, we can also find out an equivalent stiffness Ke, and we see that it is sum of the individual stiffnesses. Okay, so springs that are in parallel share the force. Notice that the fundamental equation is Ft is K of xt for a single spring, or Ke of xt when springs are either in parallel or either in series or in parallel. If they are in series, 1 over K is 1 over K1 plus 1 over K2. If they are in parallel, it is simply the sum. Once again, remember that unit of spring stiffness is Newton per meter, whereas unit of force is in newtons, displacement x is in meters. The other element that we are going to consider is a damper. A damper force is proportional to the velocity of the piston inside, or relative velocity of the two elements. Okay, so x dot represents derivative of x. Okay, dx over dt is represented as x with a dot. This force in the damper is equivalent to damping coefficient multiplied by velocity. So this damping coefficient has a unit Newton per meter per second. Meter per second is the unit of velocity. When you take Laplace transform, we have seen that when zero initial conditions are imposed, each differentiation is it translates to a multiplication in Laplace domain. When you have two dampers in series, you can find an effective equivalent or effective damping coefficient whose reciprocal is sum of reciprocals of individual dampers. That is, if this is B1, B2, when they are in series, their equivalent damping coefficient is 1 over BE is 1 over B1 plus 1 over B2. Again, we see that when dampers are in series, they carry the same force throughout. Also, when dampers are connected in parallel, you can find their equivalent damping as BE is sum of these two, B1 plus B2. And you write Ft is BE multiplied by x dot. X dot is dx over dt, which is velocity. Again, note that when dampers are in parallel, they share the force. That is, the force in damper 1 plus force in damper 2 is equivalent to force in this external force applied onto the parallel damper connection. Ft has units Newton, x dot has units meter per second, and Be has units Newton per meters per second. The third component that we consider in an SMD system is the mass. According to Newton's third law, for a constant mass body, the external force Ft causes an acceleration equivalent to d square x by dt square, and the force is equal to m multiplied by second derivative of displacement. When you take Laplace transform with zero initial condition, each derivative corresponds to one multiplication with s, and thus two derivatives corresponds to multiplication by s square. Okay. Here we say that mass of unit of mass is kilogram, force is newtons, d square x by dt square has meters per second square. We may strongly remember here that whether two masses are connected in series or parallel, it really doesn't matter as long as nothing else is in between them. The equivalent mass is the sum of two masses. Me is m1 plus m2. With that said, we will look at a simple example in the next slide. This is the system. Three elements are connected in parallel. There is a mass, there is a spring, there is a damper. We have seen that a mass contributes ms square impedance, a spring contributes k, and a damper contributes bs. So the total impedance is ms square plus bs plus k. We'll try to write it formally here. Okay, fs is f damper plus f spring plus f mass. So k times xs plus bs, we have seen that each damper contributes a s. Each mass contributes s square. For damper it is bs, for mass it is ms square. So we write fs is ms square plus bs plus k multiplied by xs. Thus, the transfer function of the system with f as the input, x as the output is given by xs over fs, that is, you take this f on this side, ms square plus bs plus k onto the other side, 1 over ms square plus bs plus k. We'll stop here to summarize. We have derived TF of a simple spring mass damper system, and we saw how to write equations from the physical principles. Impose system level constraint, that is, if they are in series the equivalent is so and so, if they are in parallel so and so. Those are all system level constraints, and we have derived the TF and we saw that it's a second order system because it involved s square. I think that's all we have for now. Have a great day.